Alrighty, everybody, welcome to Chapter 8, Chemical Reactions. It is the same chapter for honors and for college prep, and you'll see that I want you to start thinking about relationships and the different goals that we have with relationships. It's very, very important for what we're eventually going to be talking about in these videos with chemical reactions. All right, so first things first, we have to review what we talked about in the very beginning of the year. And that is that our reactions are going to describe chemical change. Now, in the beginning of the year, we started to talk about our elements, then we talked about compounds, and now we're talking about reactions. And if you remember, I made the analogy that elements are like letters, compounds are like words, and reactions are now like sentences. So we're going to describe what happens. All right, there are word equations that describe the chemical reactions, and they literally are a sentence. They use words instead of our symbols. And if we remember from what we did in the beginning of the year, the left side of a sentence is called the reactants. The right side are called the products. If you have more than one reactant, like H2 and O2, you put a plus sign between them. That plus sign really means and, not necessarily that you are adding them together. And then this arrow here is called the yields sign. And that yield sign allows for us to show that one thing transforms into another and obeys that law of conservation of mass. Okay, so here is a typical word equation. Okay, iron reacts with oxygen to produce iron 3 oxide, which is the chemical formula for rust. So you can take this whole sentence and whittle it down to iron plus oxygen yields iron 3 oxide. And because we know our symbols from that chapter, we can translate it into Fe and then O2 and Fe2O3. Okay, O2 was one of those diatomic elements, so we know that we're going to have an O2 here. Iron 3 oxide is Fe3 plus and O2 minus, and then we crisscross to get Fe2O3. Now, what do you suppose these things are? This S in parentheses, these G, and this S right here. Yep, that stands for solid iron and gaseous water, or sorry, gaseous oxygen is going to make solid rust. So it kind of tells the observer what they're going to be ready for. You know, if we have a gas over here, we want to know that a gas is coming because we don't want it to blow up in our face. So our chemical reactions show those chemical formulas. Okay, it's a lot easier to write out the formulas than it is to write out a whole big sentence. And we already spent so much time doing all of our chemical formulas with ionic and covalent bonding. So those chemical formulas are used to express those changes in reactants into products. And what we're going to start off with are these skeletal, bare bone equations. So skeletal equations tell you what, but not how much. So it is up to you to show the relative amounts by balancing them. Okay, and we'll get to that in the next couple of videos. All right, so a couple of more things to review. All right, in our chemical symbols, in our chemical reactions, I told you about the plus sign. The plus sign is used to separate them. It means and, not plus necessarily. The arrow means yields. Later on in the course, you might see a double-headed arrow or one going forward and one going backwards. They mean the same thing, and that means it's going to be possibly reversible, and that's usually in the case of solutions or gases at equilibrium. All right, and we talked about the S for solid, the G for gaseous. You guys know that. They're going to be lowercase s and lowercase g because capital S is sulfur, remember? Yeah. And then we have our L Okay, whoops, excuse me here. Our L is going to be for our liquid phase, but really we're going to use this so sparingly. The only time you're going to see a pure liquid is going to be like water, mercury, and bromine. Those ones that we colored in on our periodic table, Hg and Br2 because he's diatomic. The one that you are going to see much more commonly is this one that we went over in the beginning of the year, Aq, for aqueous. It's a solution made with water, okay? It's dissolved in water. You might see this little triangle symbol or the word heat written over the yield sign. So it'll look like this or it'll look like this. All right, and that means that you have to heat up the reaction in order for it to happen. Okay, that heat is acting as a catalyst. And a catalyst, you might remember from biology class, is the actual substance that will speed up the rate of the reaction. Okay, so from bio class, you'll remember that a catalyst is going to be, okay, something that speeds up the rate of reaction, but it's not used up. It's not a reactant, not a product. So it can't be written on this side and it can't be written on that side. It has to be written over top. It's like a step stool helping you over a fence, okay? It's not actually going to help you. It's not going to be the things that get you over the fence, but it's just going to help you get over there faster. You could get over the fence yourself, it just might take you a long time. All right, so MnO2, like when we decompose hydrogen peroxide, we're going to use some MnO2 in order to do that, and then it breaks up into H2O and O2. You might see a platinum catalyst, heat, or the triangle, not meaning change here, but it's definitely going to help you get there. All right, and what we're going to spend every chapter doing from here on out is balancing equations. Okay, each side of the equation has to have the same number of atoms of each element. That's the law of conservation of mass and matter. Okay, so we can't, uh, magically make something disappear or appear out of thin air. So when methane in our Bunsen burners burns, okay, it reacts with two oxygens and makes CO2 and two H2Os. And if you count up your number of carbons, they're going to be the same, one on each side. If you count up the number of oxygens, there's four on this side, there's going to be four on that side. And if you count up the number of hydrogens, you're going to see 1, 2, 3, 4 on this side and 1, 2, 3, 4 on this side. The mass will also be the same. Okay, you will also get the same amount on the left-hand side as the right-hand side. So 16 plus 2 times 32 will give you the same as 44 plus 2 times 18 for our masses. All right, so the last thing that we're going to do is play around with this PhET simulator, which is just so cool. Love the people at Colorado, because if you click on this link here, it'll take you to this thing right here. I already have it loaded up for you. And what we're going to see with this PhET simulator is the ability for us to visually play. Here we go. And when we visually play, you get to see how everything is going to be balanced. All right, so it introduces by making ammonia, separating water, or combusting methane like we just saw. And then it allows for you to look at different tools. I personally like having the scales here. So here's our skeletal equation. All right, we have our N2 right here, and we have our H2, and we need NH3 on the other side. So what I'm going to do is I'm going to add an N2, I'm going to add an H2, and I'm going to add NH3. Now, is that an even amount on each side? No, there's two nitrogens on the left, there's one nitrogen on the right, there are two hydrogens on the left, and there are three hydrogens on the right. So that's not going to work out. All right, so how do I even this out? If there are two nitrogens on the left side, I need to make sure there's two nitrogens on the right-hand side. So I'm going to bump this up to 2. This now makes NH3, having 2 of them. My nitrogens are even, but my hydrogens really aren't. There are 1, 2, 3, 4, 5, 6 on this side, and only 2 on this side. So 2 times what gives me 6? Or 6 divided by 2 is 3. So if I add that, voila, we are even, and you get your fun little smiley face. Okay, you can also see this in terms of our bar graph here. Some people like the graphs better. So this is not even. So here we have our nitrogen, we have our hydrogen, we have our NH3. You need at least one of each. Then you're going to put in another nitrogen, and then you're going to put in another hydrogen and another, and then it's even. Okay? So when we separate water, we can do the same thing. 2H2O, 2H2, and O2. And then we see that we have an uneven number of oxygens here. Okay, so this has 2, so I need to put 2 on this side. Now this makes 4 hydrogens, so I need to put 2 over here. If I look at the other bar graph, or the other scale, I personally like the scale a little bit better. All right, here is your H2. There's 2 H's on each side and 2 O's on each side. So I'm going to, whoops, no, that went too heavy. I'm going to add 2 on this side and 2 over here to be even. And then lastly, we're going to have our methane. And methane's going to act pretty much the same. Okay, but now we have 3 things to worry about in all these different places. When we have 1 of each, we have to make sure that we are even. So here is your carbon. Carbon is this little gray guy in here. Hydrogen is going to be this white. All right, so and then oxygen is your red. So here is your 4 hydrogens on this side. So I'm going to add another one over here. And then I have 4, 1, 2, 3, 4 oxygens on this side. So I need 4 over here. And then you can see the same thing with our bar graph here. All right. So this is really fun, especially when we start playing with the game and on our different levels. Don't time yourself. It's going to take a little bit of time for you to try to make sure that all of these are even, and you can check and see if you have the same amount of each thing. All right, so that is our PhET simulator.